Next up, Kirsten Parratt from Bioengineering on boosting statistical power, building better biomaterials.
All right.
Thank you.
Good evening, everyone. My work is in the field of tissue engineering, where we're working to move beyond implants based on metals and ceramics towards new materials that mechanically behave like real tissues and over time integrate completely with our bodies. And we can do this using a combination of cells and biomaterials. This is a great generation to be studying tissue engineering. Already, many biomaterials, like the low-friction surfaces on hip and knee implants, already let our parents and our grandparents continue to live very active lifestyles. At the same time, clinical trials involving adult human patient-specific stromal cells already are widely used. Here at Georgia Tech, my lab is heavily involved in the brand new Marcus Manufacturing Center and other initiatives geared at turning cells into a well-characterized product that can be shipped out to labs, hospitals, and companies across the country. So with all that progress, it's surprising that the field still faces a huge reproducibility crisis, meaning that when we test the same biomaterials in different labs, we often get wildly different results. And in part, this is due to small sample sizes. To save time or money, sample size is kept small, even though statistically that means your result is no better than a shot in the dark. And high sample number is necessary in order to avoid false positives and therefore waste more time and money. So that's where my work comes in. My thesis is to create a new method to analyze cell-biomaterial interactions that simultaneously lets it look at hundreds of materials of interest, but also has high sample number. And I've done this by creating these biomaterial microparticles that contain fluorescently labeled cells. Unlike competing systems, my microparticles don't require cumbersome glass slides, which means they can be grown in stir tank bioreactors like this one used in manufacturing that are controlled by computers for standardization and scale-up potential. Through Emory, I have access to an imaging machine that can collect data on thousands of microparticles each second. So I designed these size and shape barcodes along with an image analysis platform to read them that automatically distinguishes all of my different biomaterials. Then, using fluorescence data that it collected at the same time, I analyze how the cells responded to that biomaterial. Already, I've applied my process to cartilage and to bone cells, and over my last year, I'm planning to expand that to even more important tissue targets. Using my system, tissue engineers can collect data on more biomaterials and have high sample number, which I believe is going to contribute to reproducibility that'll let us bring more biomaterials from the lab bench to the patient. Thank you.